Okay, we want to get an overview of the family of exponential functions. We've seen plenty of exponential functions. We've used the function 1.12 to the t for compound interest in the context of, say, $1,000 times 1.12 to the t to calculate annual 12% interest. Lots of luck getting that, but annual 12% interest compounded annually. We've recently looked at an example of quantities that you multiply successively by 0.9. Okay, quantity falls to 90% of its value every period. And the graphs of these functions would look like this, or like this. Now let's take a look at graphs of a number of exponential functions. And any positive number b that you put in here gives you an exponential function. The one number that's not at all interesting is if you put b equal to 1, in which case y would always be equal to 1. But any other positive number gives you a potentially interesting exponential function. Okay, so table for y equals 2 to the x, there's our familiar table. And we do a table for 3 to the x and a table for 4 to the x. Very straightforward. So here's our graph of 2 to the x. Now let's go ahead and graph 3 to the x. I'll put green boundary around this part of the table and use green for the graph. Okay, 1/9. Now compared to the value of 2 to the x, when x is negative 2, 3 to the x is 1/9, which is less than half of 1/4. So you're going to be down here a little closer to the axis, quite a bit closer. Probably made that too close. 1/3 that goes with x equals -1 is going to be a little more than a fourth. So if that's a fourth, a third might be about here. And then when x equals 0, every exponential function has value 1 because any number to the 0 power is 1. So we're going to be here on the x-axis, or the 0.01 on the y-axis. And then when x is 1, y is 3. So that's going to bring the graph up to here. And then, not very well lined up, but you get the idea. When x is 2, y is going to be 9, which would be more than twice this high. It's going to be way up here. And your graph is going to look something like this. Didn't do a good job there. Should have been down below the graph of y equals 2 to the x, and then coming on up. Okay, so the graph of 3 to the x is below the graph of 2 to the x here, and then above the graph of 2 to the x here, and it gets steeper much faster. The graph of y equals 4 to the x is only 1/4 as high as the graph of y equals 2 to the x when x equals -2. It's going to be down here practically on the x-axis, or very close to the x-axis. It'll be 1/4 as high as the 1/4 mark here. And again, I'm not marking these very accurately. If you had a sharp pencil, you do better. At -1, it's 1/4. So that's going to be here, a little bit below the 3 to the x. And then at x equals 0, it's going to be 1 again. Then at x equals 1, you're going to be up here at y equals 4. And when x equals 2, you're going to be up at y equals 16, maybe way up here. And your graph is going to look something like this. Got a little too steep there, but you get the idea. Okay, so there's 3 graphs, the 2 to the x, 3 to the x, and 4 to the x. Now, we could also have values of b less than 1. Okay? So over here, b is greater than 1. We have b equals 2, 3, 4 here. Over here, b is less than 1, so we're going to use b equals 1/2 and 1/3 and 1/4. Okay, well, the graph of 1/2 to the x, and you can figure out these numbers. 1/2 to the negative second power is 1 divided by 1/2 to the second power, which is 1 over 1/4, which is 4 over 1. That's 4, and so forth. So you have to know arithmetic of fractions, but I'm not going to re-explain that. You simply have to know how to work with fractions to get these values. Okay, so when x is negative 2, y is 4. So negative 2, 4. When x is negative 1, this is for the 1/2 to the x function. Y is 2. When x equals 0, y is 1, as with all the functions. When x is 1, y is 1/2. And when x is 2, y is 1/4. So we can sketch our graph of the 1/2 to the x function. Okay, so here we have looking for a good place to label this. Yeah, I can do it here. Y equals 1/2 to the x. Okay? And we notice that y equals 1/2 to the x is just a reflection through the y-axis of y equals 2 to the x. In other words, each of these points is a reflection of the other. Each of these points is a reflection of the other. Each of these points is a reflection of the other. And each of these points is a reflection of the other. Now, y equals 1/3 to the x. Well, you might have a pretty good idea of what's going to happen. When x is negative 1, y is now 3, so that's going to put you here. When x is negative 2, y is 9. That's going to be up here among these graphs, but I'll go ahead and swap it up anyway. Excuse me. And y is 0, when x is 0, y is 1. When x is 1, y is 1/9. At 1/3. That should be up a little higher. And when x is 2, y is 1/9. So we have a graph that comes down from up here someplace. It comes through here. And does this. And this is just a reflection of the 3 to the x graph. And the 1/4 to the x graph. So this would be your graph of y equals 1/3 to the x. Graph of y equals 1/4 to the x. Well, you're going to be up at 16 here, so you're going to be way up here. You're going to be at 4 here. You're going to be at 1 here. You're going to be at 1/4 here. And you're going to be at 1/16 here. And the graph is going to come down from way up here. Pass through this point. Now actually it looked like this graph goes lower than the green graph here, but it shouldn't have happened that way. But, difficult to draw it correctly with complete accuracy given the width of the chalk. In any case, we have this graph and this graph being reflections of one another. So there's a pretty good picture of the way the family of exponential functions behaves. I could also draw one more graph. Y equals 0 to the x. Value of 0 to any power is 0. So we just have a graph whose y value is always 0. If you go for lower or higher powers of x, the graphs will follow a pattern similar to the one you see here. And for homework, you're going to get to graph some of those and make some estimates from this graph.